Hello, today we have another laboratory walk on methods of mathematical modeling. It is on the Ritz method or the Galerkin method for positive definite operator, because these two methods supply the same result for the operators of this kind, namely positive definite operators. So, using the Ritz method and the base from the previous example on the method of orthonormalized series, this base, I remind that using this base we have to enumerate the functions of this set by two subscripts, because the first subscript is going through some values and the second subscript is not more than the first one. So if we denote the second subscript j and put its bounds as 1 and I, unity is the lower bound and I is the upper bound, then the first subscript will be I plus 1 minus j. That is, if we have I equal to unity, then j is equal to unity 2, and in this case we have unity minus unity plus unity, so unity again. In this case we have unity here, and when sorry for problem with connection. Then for the second value of I, we have 1 and 2, and when I is equal to 1, j is equal to 1, 2, and here we have j equal to 1, j equal to 1 when I is equal to 2, and then 2 minus 1 plus 1 is 2, and here we have 1. And when j is equal to 2 and I is simultaneously equal to 2, then 2 minus 2 plus 1 is 1, and further we can denote this set of functions using two subscripts. It's just orthogonal set here, not orthonormal, because of these relations. So this set is more than enough for using the Ritz method and moreover Galerkin method. Solve the steady-state heat conductance differential equation of an infinite cylinder with circular cross-section of radius r with a prescribed zero temperature on the boundary, with the heat conductivity lambda equal to constant, and with a continuous volumetric heat generation Q. So we have the next equation of heat conductance with boundary conditions and with bounds defined for phi from 0 to f gamma and for r from 0 to r gamma. In these notations, we have the operator equation of the first kind with operator A defined as the Laplace operator in the polar coordinates in usual way, and the function f as the volumetric heat generation of thermal conductivity lambda. Then we find the solution in the form of partial sum of the next series. As we have seen, we use two subscript to enumerate the functions from our base. So for every function from this set, we have two subscripts, and the number of the function is I plus j minus 1. So for the first subscript I and for this first subscript j, we have the coefficient with subscript 1, because 1 plus 1 minus 1 is equal to 1. And we use this enumeration of the functions under signs, as I have already explained this enumeration. So we have this coefficient before the function of our base with subscript I plus j minus a. As I have said, the base C with subscript k from unity till 2n minus 1 because I is from unity to n and j is from unity to I, so the maximal number I plus j is 2n and minus 1 here. This base is not orthonormal, and in the case of the Ritz method or using the Galerkin method for positive definite operator of our equation, operator A, we found the coefficients A from the linear set of the set of linear algebraic equations of this form, or merely in this one. Where in brackets we have inner products in the space L2. So, what we have to do to use these methods is to calculate these inner products, as the operator A is minus Laplace operator, so here we have minus delta psi by pk, or using definition of the inner product in the space L2, this expression of this inner product. And substituting functions psi into the expression of the Laplace operator for polar coordinates, R phi we have the next second derivative Cn by dr from this function. We still have the same sign with phi. The derivative from sine is minus is cosine, from cosine is minus sine, so we have here minus, and this coefficient to the power of 2, because we have the second derivative. Here we have the derivative by r again, 1 by r, the same sign with phi, and here this coefficient to the first power by the derivative of sine. It is cosine. And the second derivative by phi. So we have the same coefficient, unity of square r, and we have this coefficient to the power of 2, j pi of phi g to the power of 2. We have the same sign here, and we have the sign. We have sine again, because the derivative from sine is cosine, and from cosine is minus sine. So we have changed the sign before this function from plus to minus. That's all. We can solve this problem in MathCAD. So what we do, we solve these set of linear algebraic equations with the inner products before unknown coefficients defined by this way. We are solving this problem for the values of bounds which are known. We put them as here. So the angle of the sector is in the bounds from 0 to pi by over 4, and a radius of the sector is from 0 to 1/10 meter. We can put any volumetric heat generation, let it be this function. Thermal conductivity lambda is equal to unity, and the right hand side of this equation is the volumetric heat generation by lambda. We put number n of the defining the numbers of functions in our base set equal to 10. It is not completely actually the number of functions, because the first subscript is going from unity to n, and the second one is from unity to I. So we have the greater value for the number of functions. Number of intervals on the coordinate r is equal to 50, and number of intervals for the angle coordinate phi is equal to is equal to 52. So we create two vectors with coordinates which are the nodes on the first and second coordinate. The 0 node has 0 value because the lower bounds of our intervals is 0, and then we define the points, the bounds of these intervals like this. Here we define the vector f1. It is discretized analog of the function f, right hand side function, and we put the coordinates of this vector equal to the function f at the points corresponding to our nodes m and n. And now we are going to put in up the right hand side functions of the set of linear algebraic equations. So here we have simply the function f by the function from our set by two differentials, dr and d phi. So we have the next components of the right hand side vector. The problem of definition of the coefficient in left hand side is more complicated because we have two subscripts, and for every of two again subscripts of our matrix, left hand side matrix, we can use in its definition two subscripts from initial enumeration. So we have for the first subscript of these matrix, left hand side matrix, I plus I and j subscripts, and for the second one m and n. So I is from unity to n, j from 1 to I. For m and n we have the same. And here we have double integrals according to the definition of the Laplace operator. I have passed minus under the sun to simplify this expression, and we have the functions of our set after this Laplace operator, this one, and two differentials here. Okay. Now we solve this set of linear algebraic equations to define the unknown coefficients A and find our solution in this form, the same form with 1-to-1 correspondence. We can also construct discretized analog of our solution in this form. So we have this series for every point of our space net with subscripts m and n. Rn and phi Rm and phi n. So we simply put here subscripts m under R and phi and n under phi, because we have defined these vectors here. Now we can see our solution. Using the sections of its private surfaces. Here we have some mistake, and the boundary conditions have been satisfied. We have zeros because of mistake of error of discretization. Here we have a bit error in definition of some private surfaces of the solution. And now we can see our solution as a surface. By the way, without transformation from cylinder coordinates to rectangular, we have this solution just in Euclidean space. Here we have one coordinate r, and here we have other coordinate phi. But we can transform with solution, taking into account that it is in polar coordinates, using the function ceil2 x, y, z in MathCAD. So this is our solution, and its physical sense is a temperature of the sector of some material with thermal conductivity lambda equal to unity, and with volumetric heat generation defined by this function. We can change this function as we wish. Now let's solve this problem in Visual Studio in C#. I'm modifying our library methods var where we have already have orthonormal series, and now we add a Ritz seal, the Ritz method in silent coordinates, or simply in this case in polar coordinates. Well, we have added a new class in this library methods var. We have renamed it into Ritz seal method, and let's get started to realize this method in polar coordinates in common. So we have to use static variables and methods, and of course fields, of course properties. Here are fields, here are properties, and here are methods. Because the built-in functions of C# deal with static arrays. So we have the number of functions, number of intervals for the coordinate r, number of intervals for the coordinate phi. We have these coordinates itself. We have coefficients a, which are to be defined, curve Ritz. We have two-dimension the matrix two-dimensional array series Ritz. This one, and we have extended matrix, which is the left-hand side matrix B, square matrix, plus the right-hand side vector F. The matrix constructed in this way is called extended one. And a good style of programming is to use private fields. Here are implicitly private fields because we have missed private word explicitly. It is the same, and here we put public static methods, static properties corresponding to these fields. They have the same names, but they begin from uppercase letter. So we put these methods here, number of intervals R, number of intervals phi, R phi, coef Ritz, series Ritz and extended matrix. Series Ritz and extended matrix. Now we are realizing the methods. The method to solve this problem in cylindric coordinates. Our input parameters are the number of functions and two bounds, R-bound and R-bound and phi-bound, and right-hand side function. Having right-hand side function in the form of this matrix, we can get the number of intervals MR and M phi. As we have this matrix as input parameter of this method, we can get upper bound for the first, here 0 direction, and upper bound as a subscript for the second, here first direction. The number of points is always more by 1 than the number of intervals, so we have two arrays R and phi with the number of components from 0 to number of intervals plus 1, because from 0 to number of intervals, it is number of intervals plus 1 for R and phi coordinates. And we create arrays for Ritz coefficients, which are to be calculated. Its number is two number of function. We keep in mind that is not completely number of function, it is number n. So we have 2n minus 1. And here enumeration is from 0. So the two number of functions without unity. And we have extended matrix. Here we still have two number of functions in this matrix, enumeration of rows and enumeration of columns, two number of functions plus 1, because we have added the right-hand side column, right-hand side vector to the left-hand side matrix, and so we have got extended matrix. And we have a Ritz series matrix, this one, with number of points from 0 to mr and from 0 to mv. So number of intervals plus 1, number of intervals phi plus 1. Here we calculate vectors r and phi to avoid passing them as parameters of our method. We calculate right here, and we will calculate them again in some place of the code where we are going to use this method. I repeat, to avoid magnifying number of parameters of this method. We initialize extended matrix as 0 matrix for a while, and here we define its last column, namely the vector of the right-hand sides of the equation of our set, this one. So according to this expression, we have I from unity to n, j from unity to I. First of all, we put the current value equal to 0 because we have the sum here, sum operator here. We have double sum by m and n, m from unity to number of intervals r, mr, and from unity to till the number of intervals phi, m phi, and extended matrix is extended matrix plus right hand side function mn by first sign, this one, and by the second side by two differentials, r, dr, and d phi. Now at it is more complicated part of our code. We have to put this expression into the rest of this matrix B, extended matrix. So it is simply arithmetical exercise. And what we need it is our attention to avoid some errors. I have checked, that's right. And as we are going to use the Gauss method to solve the set of linear algebraic equation, we have to avoid zero coefficients on the mean diagonal. To do that, we put the coefficient B00 equal to unity. Here you can see that. Have zeros here, and put B equal to unity. Otherwise, we will have error using Gauss method. So I add if extended matrix 0, 0, if equal to 0, extended matrix 0, 0 is equal to unity. Now we use Gauss method. To do that, we have to add the reference to the library with method slide. I have created it before, and we simply use it. And we have to add the reference to the namespace, corresponding namespace method slide, which is in that library. So we use Gauss method, and we initialize the Ritz coefficients, the coefficients of the Ritz method as the solution of our set of linear algebraic equation found by Gauss method, the Gauss method. And here we substitute our coefficient into desired solution U. We substitute them here. So we have our curve Ritz I plus j minus 1 plus first sign r gamma by second sign j by phi n by phi bound phi gamma. So that's all. Now we are going to create, we are creating test application, which will be Windows Presentation Foundation application. Every application of such a kind have some XAML file where we have some design of our presentation. And here is behind file with definition of the code corresponding to some events in our presentation program. Here we add one button from this panel. We simply drag and drop the button to here. Then you on it, put here its name, button start, and content, which is at the bounds of this button. Here under lightning symbol, we have different events. And double clicking this event, open the method which is event handler for this event. Click. All we have to do is get our solution for our problem and create files. And when our work is completed, we create message box which inform us of the files were created. The methods get solution is simple enough. We put here the values from our Mathcad program. Phi bound is pi by 4, R bound is 1/10. Also, we have a right-hand side function f and two vectors r and phi. We define these vectors again according to these expressions. And here we address to our static Ritz cylindric method for definite parameters number n, 10, mr and m50. Number n, r bound, number n, r bound, and phi bound, and the right hand side matrix f. So we get our solution for these parameters corresponding to our Mathcad problem. Now we use use construction try catch to create the files. I already explained it in the previous works, so now I skip this explanation. We just create file for the vectors r and phi. We create file for extended matrix and for desired Ritz series. Well, now we do this application active and can try create our files. Start work, our button. and the files were created. Our message box. Okay. We close the application. The work is completed. Now we open Excel from Microsoft Office. Excel. And import our data from the text. We're going to our library, methods var, Windows Presentation Foundation application to test Ritz method in cylindrical coordinates, bin, debug. Now we have to import vector R, that's right, and vector phi. And our Ritz series for each point of the space net. Okay, we have homogeneous boundary condition, as you can see, zeros. And this is our solution. If we use this solution without plus transformation, then we have the same here. So we have got the solution of this problem. For the heat conductivity equation, both in MathCAD and in the C#, creating the library for this method, and using additional technique of creating the Windows Presentation Foundation application, which tests our method to solve this problem. The physical sense is hitting some sector, space sector, with in volumetric heat generation and with boundary condition. To use homogeneous boundary condition, we have to transform the absolute temperatures into some effective temperatures. Such that the temperatures, the least temperature of at the boundary is equal to 0, something like this. So today we complete our work. Thank you and goodbye.
Thank you.